Hey students, this is Mr. Bob. This video is about topic 3.2, modeling a gas. Before watching this video, you should have completed a first pass of the focus note taking on sections 13-6 to 13-10 in G and Coley. Have those notes in front of you with something like a pencil, and have a colored pencil or highlighter ready, because the idea here obviously would be that you would add to the notes, fill in, clarify stuff as you see fit. Before we get started, first a joke. We all need more humor these days. What did the basketball coach say to the player when the player asked, "Coach, do you think we'll win this game?" The coach said, "I certainly hope so." I know that if you are watching right now in class or in Zoom, you would unmute and laugh heartily. Okay, here we go. So what I want to talk about is the following. Come on. There we go. Just a couple quick recommendations. Remember to avoid mindless copying. Stop and rewind the video as you need to. Also listen at 1.5, 2 times speed if that works for you. Actively listen and selectively write. Things that are emphasized by me or things that you feel like are important, please abbreviate. That's a good way to take notes. It's important, helpful. If I give you a sample problem and you'll get some here, please go ahead and pause the video. Take at least a minute to try and work through it yourself. Make your brain struggle. If you're still confused after watching the video, please highlight that point of your notes and point it out as a point of confusion, POC, so that you can make sure you bring it up with a classmate or with me later on. Okay, here we go. 2 essential questions. What are the key assumptions of the kinetic model of an ideal gas? And the second one, how can we apply these assumptions and the ideal gas law to real-world situations? Let's get right into it. If we look at a molecule, let's look at this gas molecule that's confined in a closed box as shown. What's going on here? Well, you can see that the molecule's direction is changing pretty frequently. So if something is changing direction, we know from kinematics and from forces, Newton's laws, that if it has an acceleration, which it clearly does, anytime it hits the wall, then there's a force that it feels. So the walls are exerting a force on the molecule, the walls of the box. By Newton's third law, if that's happening, then the molecule is at the same time exerting a force on the walls of the box. Okay? And so if that's the case, we can quantify that. Okay? And we can quantify that in a way. We use this concept called pressure. And this concept called pressure is used to kind of give us a formal way to calculate and measure that and compare it in situations. So the pressure, for example, the pressure felt in a closed box where a gas is moving around it is the force per unit area. And this pressure calculation or pressure equation is true in all situations, not just the one I just mentioned, but this is the one we're talking about here. The units are always important, okay? The unit on force is the SI unit, the Newton, and the unit on area is meters squared. So the SI unit for pressure is newtons per meter squared, which is also known as a Pascal. Quick practice problem. A 150 kilogram person stands on one foot on some ice. Given that their foot is about 9 centimeters by 10 centimeters in rectangular cross section, find the pressure on the ice. Again, pause this video for a second, see how far you can get on this. Okay, let's keep going. So the solution is, first you find the force, and in this case, it's the weight of the person. 150 kilograms times 9.8 meters per second squared gives you that force. You find the area. The only trick there is you have to convert from centimeters to meters. Okay, so you get that number, 0.009 meters squared, and then you divide the two numbers by each other, and notice you get 160,000 pascals, big number. Okay, and that's fairly common. Okay. So keep that in mind. Usually when we look at pressure like atmospheric pressure, we talk about it in terms of kilopascals because those numbers are pretty big. Okay, this next slide lays out some really important information about the kinetic model of an ideal gas. And this is also known as postulates of the kinetic theory. And you'll also see it referred to sometimes as the kinetic molecular theory, KMT. So here we go. Normally I say on a lot of these things, hey, don't memorize this. Just understand the concept. This next slide is actually one that I strongly recommend you memorize. It doesn't have to be memorized word for word, but you have to be able to just know the 4 assumptions. So here they are. Okay, so an ideal gas is an imaginary gas that is used to model real gases, and it has assumed to have these 4 properties or these 4 assumptions. The first assumption is that the gas has a really large number of molecules, and they're all moving around in random directions at varying speeds. The second one is that the molecules are far apart from each other. Their average separation is much, much bigger than the diameter of the particles themselves. The third one is that there are no intermolecular forces between the molecules, okay? Meaning one molecule does not exert a force on another molecule. The molecules only interact with each other when they collide. In other words, what I'm saying in terms of the language we used last in one of the previous videos is that the potential energy is minor or pretty much zero. So all the internal energy of the molecules is kinetic energy, is another way of saying that. And then finally, the collisions between the molecules with the walls of the container and with each other is perfectly elastic. And what does that mean? Let's just make sure we understand what an elastic collision is. This is something we talked about in last year's physics class. Elastic collisions are ones where the kinetic energy of the system is conserved. So there you have it. Those are the four assumptions. Again, these four assumptions are definitely things that I would memorize. So make sure you do that. Okay, the kinetic model of an ideal gas. If you look here, what I have here is a scenario that I want to walk through. Notice in one scenario, the molecule is moving slowly. Its kinetic energy is lower than, say, in the middle one. You can see that's reflected in the temperature. The thermometer has a low reading, and then it has a slightly higher reading. And then in this case, the one in the box, the molecule is moving really fast, and the temperature, as indicated by the thermometer, is high. So what we have here is we have low temperature, medium, and high temperature. Okay? So just as temperature was a measure of the random kinetic energy of the molecules for solids and liquids, so it is for an ideal gas. Same idea applies here. Okay? And so what happens here? If the temperature of the gas increases, so does the average speed and hence the kinetic energy of the molecules. Right? So let's just remember that. Okay? This is a key idea, key underlying assumption that helps us understand the slides that follow. So now we're going to go through a series of scenarios. We're going to look at three variables: pressure, temperature, and volume. We're going to keep one of them constant, and we're going to see how the other two are related when two of them are kept constant. So let's first talk about how pressure and temperature are related when the volume is constant. Well, in this first scenario, notice these three boxes, they all have the same size, same volume, but as I showed in the last slide, they have a different temperature. Low on the left, high on the right. How is that related? How is the pressure going to be impacted by this? Well, if you think about it, the number of collisions per unit time that the boxes are experiencing vary greatly. The one on the left is experiencing very few collisions per unit time as compared to the one on the right, where there are a lot of collisions per unit time on the walls of the box on the right. So in other words, the walls of the box on the right are feeling greater forces and therefore a greater pressure than the walls in the box on the left. So we can conclude here that as temperature increases, so does pressure. So we say that pressure and temperature are directly proportional, and that is actually attributed to law. That is a law that's attributed to scientists from a long time ago. Gay-Lussac was their name. You'll sometimes hear it called the Gay-Lussac law. I don't expect you to know the names of the laws. I just expect you to know that pressure and temperature are directly proportional when volume is constant. Next, we're going to look at how volume and pressure are related when the temperature is constant. So if you look here, I have a small volume box, medium volume box, and a large volume box, and notice the temperature is the same. And they are meant to be moving at the same speed. It might not look the same, but the other ones, the one on the left might look to be moving faster just because it's hitting the walls more frequently. But assume these are the same speed, same kinetic energy. So what's going to happen here? Well, if you think about it, in the smaller volume, the molecules have to travel less distance to hit a wall, so they're hitting the walls more often. That's clearly evident from this animation. So if it's hitting the wall more often, that wall is experiencing greater force per unit time than the box on the right, for example. So in other words, the pressure is bigger on the left, the pressure is smaller on the right. So it looks like pressure and volume are inversely related to each other. In other words, a smaller volume gives you higher pressure, larger volume gives you lower pressure. And so this is called Boyle's law. And again, I don't need you to know the names of the laws, although we are going to do more with Boyle's law. You're going to do a little experiment on it. Pressure and volume are inversely proportional. Okay, let's go to the third scenario. How are volume and temperature related when pressure is constant? To help us understand this, I think it's important to do a thought experiment in the classroom. I would show this to you. You could also do this at home, actually. If you have a balloon, and you have like a pot where you can put some warm water, and bring it close to a boil, Just fill it up with a little bit, just so there's like steam coming up on that balloon. What you would find is basically if I put that balloon in that situation there and I turn on that hot plate, what's going to happen? Well, I think we all know, maybe we don't, but you would observe it if you were in class. That balloon is going to expand, okay? And it's going to expand. In other words, the volume is going to go up. So what's happening here? Well, as the temperature increases, the molecules inside that balloon are moving faster, okay? And so pressure then is going to, the pressure is going to remain constant because what's going to happen is the walls of the balloon are going to expand because it has to equalize the pressure because it's still at atmospheric pressure. It's at sea level. So the pressure is staying constant. But then because the pressure is staying constant, as the temperature increases, what is changing? And clearly the volume of the balloon is changing. And so this basically causes the volume to increase as the temperature increases when you have a constant pressure. So the pressure stays constant, but the way it stays constant is by expanding the volume of the balloon. Okay? So we can say volume and temperature are directly proportional because if the temperature is going up, the volume is going up, as you can see in these drawings. And so this is what's called Charles's law. Okay, let's talk about the mole and molar mass. If you recall from the periodic table, elements have certain numbers associated with them. And that number here, this guy right here, okay, this is what we call the molar mass. And before we get to it, let's just make sure we establish one of the basic SI units is this idea of a mole. And if you recall, the mole is the number of atoms an element has that will have a mass in grams equal to its gram atomic mass. That's kind of a mouthful. And I'm just going to want you to just kind of think about, understand that that is, the next slide will explain this better. Okay, but this is kind of like the formal definition. Okay, so if you want to find the mass in 1 mole of carbon, basically all you would do is, from the periodic table, you could see there that the molar mass is given there on the bottom, 12.011 grams or 0.02011 kilograms. So that's what we call the molar mass of carbon. Now, why do we do this? Let's talk about that. The important idea here is that a mole of carbon and a mole of phosphorus have the same number of atoms, okay? A mole of any sort of molecule, or excuse me, element from the periodic table has the same number of atoms, okay? So this means that the phosphorus, a mole of phosphorus, which has a different mass, is still going to have the same number of atoms as a mole of carbon. Okay, and that mole number is what we call Avogadro constant, 6.02 times 10 to the 23rd molecules. By the way, if I haven't said it already, you are going to be getting a data booklet, kind of like the equation sheet you got in the first year class, but this is one that's standardized for IB exams. And this number will be one of many constants that you get on there. So you do not have to memorize this number, you just have to know where to find it on the data booklet. Okay, so basically, if you want to figure out the number of atoms in a sample, all you have to do is basically take the mass of an object and then convert it to moles and then use the conversion that 1 mole is 6.02 times 10 to the 23rd molecule. So here's an example problem. How many atoms of phosphorus are there in 145.8 grams of it? Again, pause this video and try and work this on your own. Okay, what do we have? Well, what we're going to do here is you start with a given quantity, 145.8 grams, and then from the periodic table, you know that this is the molar mass of 1 mole of phosphorus. So you put the grams on the bottom so they cancel. And then convert from moles to atoms, you use Avogadro's number. 1 mole is equal to 6.02 times 10 to the 23rd atoms. This is really a factor label unit conversion of sorts, you could think. You could think of it that way. This cancels with that cancels with that. And we get 2.83 times 10 to the 24th atoms. Okay, this next formula can be really confusing because there's a whole bunch of n's in it. So I'm just going to make sure we understand what's what. Okay, so when we look at this lowercase n in IB lingo and in other systems too, this is number of moles. This capital N is number of atoms. And N sub A we know as Avogadro constant. So here's an example. A sample of carbon has 1.28 times 10 to the 24th atoms as counted by Marvin, the paranoid android. You're going to see Marvin in a second. The question is, how many moles is this? And what is its mass? Again, pause the video. Try and work on it yourself. There's Marvin. The answer, A, all you do is you take the number of atoms, you use the conversion that 6.02 times 10 to the 23rd atoms is 1 mole, and you get an answer just over 2 moles. What is its mass? You just take that answer in moles, multiply it by the molar mass given to you by the periodic table, and you get the number of grams of carbon. All right, we're getting close to the end here. Ideal gas law. This is a hugely important idea. Okay, so if you've been kind of not paying too close of attention, please pay attention now. The ideal gas law. It's called the equation of state for an ideal gas. Okay, and it basically flows from the assumptions we talked about with the 4 assumptions of the kinetic molecular theory. And it is this: basically the pressure of an ideal gas times the volume of an ideal gas equals the number of moles of the ideal gas times the temperature times something that's called the universal gas constant, and it's given the letter capital R, and it's got a value there you can see. So let's just remember pressure is measured in pascals or newtons per meter squared. Volume is measured in meters cubed. And the temperature is measured in Kelvin. I just want to pause on this point for a second. I want to emphasize this point. When students work problems that require them to use the ideal gas law, the most common mistake they make is they fail to convert the temperature that might be given to them in Celsius. They fail to convert it to Kelvin. Don't make that mistake. So again, the most common mistake, if you get a temperature in Celsius, you have to convert it to Kelvin before you start doing calculations. Okay, final slide. A useful way of thinking about the ideal gas law. Notice PV equals nRT is listed up there in the right corner, but I just wanted you to think about this idea because this can be super useful in solving problems. If a system is closed, and most of the problems you're going to get, in fact, I can't think of one that isn't going to be given to you where the system isn't closed. So in terms of like a calculation problem, okay, if the system is closed, then the number of moles will remain constant. So if that's true, then N is constant. And we already know that R is constant. So if I'm trying to compare a before-after situation, which is often what these problems are, okay, you might have at the beginning, P1 equal V1 equals N1 R T1. And then afterwards, you might have P2 V2 at some final state equals N2 R T2. Okay, but if N1 equals N2, then watch what happens. If I just take this equation and divide it into the other equation. So what I'm going to do here, watch this. P1 V1, and underneath I'm going to put P2 V2. Okay, and then here I'm going to put N1 R T1, and underneath it I'm going to put N2 R T2. Notice I've just taken one equation divided by another, and you can do that. This is allowed. Watch what happens here. So we said N1 and N2 are the same, right? So these cancel, this cancels, and these two R's cancel. And if I do some rearranging, I'm going to put all the initial states on one side, all the final states, the P2, V2, and T2 on the other side. I get this equation. Let's go over here with this. So P1, V1, I'm going to bring the T1 over here. P1 V1 over T1 equals P2 V2 over T2. This is a very useful way to think about the ideal gas law when you're given like a comparative scenario analysis, which you will often be given, okay? Because it can be incredibly useful, and it lends itself to proportional reasoning, which is something that you have to do quite frequently. Okay, that's the end of this video. I hope you enjoyed it, and keep up the good work.